We've got a pump that's operating at 80% efficiency, and it's delivering 30 gallons per minute of water from a reservoir to an open-air storage tank at a chemical plant that is 1 mile away. We're using 3-inch Schedule 40 pipe, and the frictional losses are given to us as 200 foot-pounds force per pound mass. The elevation of the liquid level in the tank at our chemical plant is 873 feet above sea level, and the elevation of the liquid level in the reservoir is 928 feet above sea level. We got two questions here. What is the minimum horsepower required for the pump? Second question is, the elevation of the reservoir is fixed, but what elevation of the liquid level of the tank at our chemical plant would make the pump unnecessary? So we've got some information here. 80% efficient pump using a nominal density of water of 62.4 pounds per cubic foot. Our flow rate, our elevations here, our head losses. Notice that these are on a mass basis, and our Bernoulli equation, we prefer to use a weight basis, so we're going to have to do a unit conversion there. But part one is find the minimum power required for the pump, and then part two, of course, is, well, could you get away without having any pump? Could you just use gravity? Notice the elevation, 928 feet to 873 feet. Why can't we just use gravity? Well, the answer is that we cannot use just gravity because there are frictional losses that have to be overcome. This is 1 mile in distance. Usually when we think about siphoning fluids from one, transferring fluids from one tank to the next, we're thinking about things that are relatively close together with very short sections, relatively short sections of pipe. Here our pipe is 1 mile long. So that builds up a lot of frictional losses, and you can see that that value is 200 foot-pounds force per pound mass. And so you will need a pump for this, the way this system is set up initially. The second part of the problem says, well, what if you could change one of the elevations? Of course, we can't really make the reservoir higher practically, but we could make our tank level lower. And so we, for example, we could just physically move it to a section with a lower elevation, or we could dig a pit and partially bury that tank. So at what point would we be able to do that? Well, let's look at the first part. Find the minimum horsepower required for the pump. And so what I like to do is I like to write my Bernoulli equation. I've kind of already started. I've identified how my energy balance is going to be set up. Position 1 is going to be the surface of the reservoir. Position 2 is going to be the liquid surface of the tank, and it's going to have the pump in here. Notice, of course, this is not drawn to scale, just a representation. So here's my Bernoulli equation. I like writing it in the full form, and then what I like to do is go through and start applying my assumptions and given information to see how this will simplify. So this is steady state flow. Water's incompressible, so constant density. Let's start looking at these terms here in the equation. P1, this is atmospheric pressure, right? P2, we're told this is also open to the atmosphere. And so we're going to assume that there's no atmospheric pressure differences between these 2 points, and so these pressure head terms are going to cancel each other out. What about the velocities? Velocity at position 1, that's the surface of the reservoir. Is that going to change? No, and even if it did, it would be so slow that it's not going to matter. So velocity head at position 1 is going to be 0. What about velocity head at position 2? That's also going to be 0 because, again, this level is going to be relatively constant and barely change at all. Elevations. I'm going to set my datum to be the sea level, right? And so if you like, you could set the datum to be the level of the tank, but again, we're going to be solving for the tank level later, so I'd rather just keep everything consistent by setting my datum at sea level. So Z1 is going to be 928 feet. Z2 in the first part of the problem is going to be 873 feet. So that takes care of those terms. What about head added? Well, head added, this is going to be our pump. And so that's what we need to calculate. That's going to be our unknown in the first part of this problem. Is there a head loss term? Yes, that is actually given to us. All right, we're given no details about the piping or, fittings, couplings, whatever else is needed, expansions, contractions that are needed for these. So we're just given this number, but notice this is on a per mass basis. And so we're going to eventually have to convert that to, because in this equation, head loss is a per weight basis. So we're going to have to make that conversion. And then head extracted, there is no head extracted. This gets crossed out. So using those simplifying assumptions, we can take the Bernoulli equation and simplify. This is what we get on the left side, the right side, and then we solve this equation for the head added. And this is the equation we get. We know Z2, we know Z1, and we're given the head loss, but we need to do some dimensional analysis of it. So convert the head loss from a mass basis to a weight basis, and we do that because if it's per mass and we make it per weight, we need to multiply that mass in the denominator by G. And so that's the same as dividing by G, but then we need to multiply by G, that whole thing by GC. And so the nice thing is, of course, since we're working at sea level, basically at sea level, G is equal to GC. And so it turns out that our numerical value for the head loss is the same as, on a weight basis, is the same as our head loss on a mass basis. But notice that it's incorrect to just say pounds force, cancel pounds mass. You really need to go through and make sure you remember that GC is a conversion factor that allows us to do this conversion. So make sure you mind all your P's and Q's while you're doing that. So now we've got everything on a consistent unit basis, and so we can solve for head added. So head added is going to be 145 feet. Head added is 145 feet. So this is the amount of head that our pump, the amount of energy per weight that our pump has to add to the water that is going from reservoir to tank. 145 feet of head. Well, what does that mean by power? Well, the way to convert head to power is to multiply, look in your notes, is to multiply by rho times G times Q. That equals power. But we also have to realize that some of that energy from the pump, some of that power from the pump is getting wasted. All right? And so our efficiency of the pump, if I remember, is 80%. And so we have to divide by that efficiency. And so the minimum power required for that pump is about 1.374 horsepower. Does that seem realistic? That's not a very large motor, is it? You probably want to have maybe 2 to 3 horsepower to take care of your installed power. So anyway, is that? I mean, that's smaller than most lawnmower engines. Could that really be all the power you need to pump water over a period of a mile? Well, in this case, yeah, I think so, because remember, we do have a pretty sizable decrease in elevation difference. And remember, we thought when we first looked at, well, why can't gravity do it? Well, gravity can't do it because of the friction, right? But the friction isn't that big. I mean, it's big enough that it won't let it happen spontaneously by itself without any power. But anyway, so you don't need a big motor to do this. Now, the second part of the question is, well, what if we don't want to use any motor? What if we just want to have gravity do it? So how far are we going to have to lower the tank? Well, you can do this problem one of two ways. One of the ways is you can do this by kind of noodling through it and just thinking about it, how this will work. So if we have 200 foot-pounds or 200 feet of head is in friction in our piping, right? What's the elevation difference that's going to have to balance that 200 feet of frictional losses? That's 200 feet, right? And so 928 minus 200 would be 728. If this tank surface could be lowered to 728 feet, then water would be able to just start flowing. So 727.9 feet. Water would start flowing just by the force of gravity from the reservoir to the tank. And so you can kind of think through that in a more qualitative approach, or you could actually go through the Bernoulli equation, and we could look at the Bernoulli equation, and what it would give us is that Z2 is equal to Z1 minus head loss. And you can go through and convince yourself of that derivation, and we get Z2 is equal to 728 feet.